You're listening to Würth Elektronik's What's Up radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik specialists who are going to shine a light on some interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast. In today's episode, we are back to focusing on EMI, but this time we're going to take a look at the crucial topic of the modern EMI shielding technology, as well as different techniques. Now, as we've discussed in previous episodes, as well as in our webinars, EMI is electromagnetic interference, and it can significantly impact the performance and the reliability of a bunch of sensitive electronic devices. And this makes it essential to understand how to prevent these interferences. In this episode, we're going to cover a range of practical strategies for mitigating EMI, focusing on both housing and PCBs. We'll also discuss the latest advancements and the best practices in shielding techniques to ensure your electronics remain robust and interference-free. And then finally, we're going to take a look to the future, addressing how emerging technologies like 5G and IoT, as well as industrial IoT, IIoT, how they are bringing new challenges to EMC. We'll explore how these innovations impact EMI and what solutions are being developed to tackle these issues effectively.
So first of all, I'm going to start to explain some basic principles or basic terms that we need to know about shielding materials. And then I will directly jump into the topics about giving tips or giving advices for using the different type of products that they are related for the shielding materials. Like in this case, for example, it will be the EMC gaskets, as you can see here. Then also about the EMC tapes. Then I will jump into the topic about the board level shieldings, and then finally, I will give some tips about the magnetic absorbers in this case. Well, first of all, about the shielding in this case. So why do we need shielding materials? Well, the answer is pretty easy. At the end, we have an environment full of different fields, or like in this case, electric fields, magnetic fields, or the joint of both of them, in this case, the electromagnetic fields. And then those are working in several or in different frequencies. Like, for example, we have about the mobile phones data, then we have also about the IoT in the industry, and then also we are going to face currently or in the next years about the 5G frequency ranges. And then all of this, or this environment, it is pretty loaded currently, as I commented. And then this at the end can provoke several problems, especially in our hand devices like we have. Like, for example, it would be like a phone, or maybe your Apple Watch, or maybe some other device that you have. And then these malfunctions at the end can provoke that your device is not working as it should work at the end. And then also because at the end, you need to fill it out, or your devices need to fill out some certificates in order to pass or to be able to be sold to the customers. Then one of the first things that we need to have clear, it is about what can provoke, in this case, problems here. At the end, the basic thing, or just going into the basic, is an antenna. An antenna will be like the root to all the problems that you could face in this case. And then an antenna can be like something pretty big that you can find in the outside, like let's say like the big TV antennas or communication antennas. Or if we go a bit more into our devices, it can be something really basic, like for example, an input-output interface or a cable, or also it can be like some traces from your PCB, or even some of the ground planes, or even a small thing like a bias. And then also it is not only like something really physical or like something that you create into your PCB. Also, we can find over there or that can provoke an antenna. It can be like some basic components, like in this case, a heatsink, that at the end, it is something that it is only to dissipate heat. Then another important thing that we need to clarify about shielding materials, it is about how you can quantify them, or how can you say that one shielding material is better than the other one. In this case, one parameter that we the engineers define it in this case, it is the shielding effectiveness, which at the end, it can be also named as, in this case, attenuation, or the definition of it will be how good it is, the material, in order to attenuate or to, in this case, eat or remove the electromagnetic field. And then the mathematical definition about this parameter, it is pretty simple. It is, in this case, let's say, at the end, it will be the measurement of the environment without the shielding material versus or minus the measurement of the electromagnetic field of the environment with, in this case, the material in the middle. So at the end, we could have the real value about how much it will be attenuated. Then some basic rule of thumbs about how more or less how to control or which material do you have to use. In this case, will be that, let's say that you have let's say, a damage or a bad electric field that you want to attenuate. So then in this case, what you will need to use will be a high conductivity or low impedance material. Like, for example, it can be like the traditional copper tape, as you can see here, or even the aluminum tape. Then, a good thing here is that the thickness of the material doesn't matter. So for example, you could go to a really cheap and thin layer of aluminum tape that you can just stick it over an area, and then it will automatically it will react to the electric field by attenuating or by absorbing it. And then it will happen the same if you use, for example, a copper tape or even the conductive fabric tape. So the main thing here is to look for a low impedance material. But then let's say that we go to the other side of the street. And then instead of attenuating or looking to remove an electric field, what we want to remove in this case is a magnetic field. So then in this case, we don't want something that it has a low impedance. What we are looking in this case, it is something that has a high value of permeability. The main thing here is that the permeability, it is the capability of the materials to, let's say, play or to interact with the magnetic field, meaning that the higher the value of the permeability that it will be, the more that it will be able to play with or to interact with. And then here, normally there is also like the rule of thumb that says that the thicker the material so from the magnetic field, so it will be the thicker the material, the better. That's normally like a rule of thumb that we normally say because it will attenuate more in this case. And now we are going to jump directly into giving tips about how to use the different products. So one of the main products that you can find in order, once we are looking for shielding materials in this case, it is EMC gaskets. Then EMC gaskets at the end, they can be found everywhere on your device. It can be, for example, like on the housing, when you have like a door or a lid that you need to close it. Then also it can be used on the EMC chambers, as you can see here, or even on the input-output interfaces, just to connect the cables. And then you can already start thinking or seeing the pattern around here. That is that EMC gaskets at the end, they are being used when you need to make contact between two metallic surfaces, or they are being used in order to fill gaps here. Because once we are placing like two metallic surfaces between and making contact between them, then we may think that, yeah, everything's super soft, everything's super smooth, so then I don't have any kind of discontinuity here. But that's not what is happening. And then if we get a microscope and then we're making zoom in, then we can see that we have like some small gaps or A gaps here that they will act as an open door in order to the noise to go to the outside or the noise to go into the inside. So here, let's say that this is the housing for your device, and then you have your PCB here in the inside. So then if we are not using an EMC gasket, that means that the electromagnetic noise or the electromagnetic field that is in the outside, they can go into the inside, and then it will affect, in this case, your PCB, or the PCB, if it is creating a lot of noise, then it can go to the outside, and then you will fail, in this case, the EMC test. And then let's say that the big summary here is that what we want with our housing is at the end to have a perfect parallel box that is fully closed. But that's not something that we can reach, especially if you reach out your colleagues that they are mechanical engineers, because at the end you will have ventilation holes just for the lids. You will have like you will have to put a display over there, so then it is not reachable. And that's what you need to use in this case EMC gaskets. Because then let's say in this case that we have the door or the cover. So then if we are using the EMC gasket there, then we will be able to fill all of those gaps with conductive material, this case from the EMC gaskets, and then we will be able to have a thing that is pretty close to a perfect parallel box. So then what we will avoid in this case will be to the noise to pop up to the outside or the noise from the outside to pop into the inside of our device. Then another important thing here, it is for the EMC gaskets is that normally there is also like another rule of thumb. So I'm going to, during this webinar, I'm going to say a lot of rule of thumbs because at the end it is the most useful thing because it is what we are looking for. That once you are designing your device, that just to have like some guides to later just go more into details. So the first rule of thumb in this case for the EMC gaskets, it is to compress them normally around at 20%. Then why we are saying that we need to compress the EMC gaskets around the 20%, because that's normally, let's say, the sweet spot where the gasket can offer the best parameter about conductivity, so the lowest RDC or the lowest impedance point or value. And then at the same time, you are not overstressing mechanically the gasket. So meaning that the material in this case, so the foam in the inside or the metallic material is not overstressed, meaning that you can compress and uncompress it like more times. Once if you are compressing it the 20% more or less. Then at the same time, it is really important to compress them around 20%, maybe a 30, depending on the height of it. Because for example, one traditional and one really common gasket in this case, it is the conductive fabric over foam gasket that I will explain in more in depth later. And they have a non-conductive adhesive tape in the middle, meaning that if you compress them around 20-30%, what you will achieve in this case will be to the conductive material, in this case, this gray area around here, you will be able to make it overlap the non-conductive adhesive, ensuring that you will have a good conductivity between the bottom surface and the top surface. Another tip in this case will be that if you are still on time, reach out your mechanical engineer and then ask them to design a small groove in the inside of the cover or on the frame. Mainly because by doing this, then you will be able, in this case, to fit the EMC gasket, and then you can just leave enough space just to compress it the 20%. So meaning that the depth of this groove, it has to be around normally an 80-70%. So then you are leaving, in this case, the 20%, 30% exposed to the outside. And then once you are compressing it downside, then you are ensuring that you are not overstressing mechanically, in this case, the gasket. You have a good parameter of conductivity. And then also at the same time, you're ensuring that the gasket won't move. Because if you place it like this, just without leaving like any kind of groove, if the gasket is really thin and tall, then what could happen is that the gasket will just slip out, forming here like a kind of an L to the outside or to the inside, making it that probably you won't be able to ensure that you will have a good conductivity between the top surface and the bottom surface. Then another important thing here is that normally in order to ensure that the gasket is placed like quite smoothly or that the surface they are not provoking like any kind of abrasion, there are some cases where some greases are being used. It is not really recommendable to use them, mainly because at the end you are adding another chemical thing into the mix between the metals, and then also normally they are non-conductive greases. So meaning that you could provoke that maybe some grease will get into the surface between the gasket and the metallic surfaces, making you to have there an open and also not achieving actually this goal here. Then also, as I commented about the compression, it is quite important. And that's why we have also a red expert model where over there you will be able already to see how much force you need to compress the gasket. In this case, it will be the top chart. And then also how much force is the gasket doing against your device, which in this case will be the bottom chart or the bottom trace in this case. And then on the right, what you will be able to see in our red expert module will be the RDC chart. So then this is actually a live measurement, which we did, which is just to compress the gasket. So then you can see that once we are compressing it between a 20% and a 30%, which will be more or less this gap here, we are already achieving, in this case, the sweet spot or the best value of conductivity. And also, that's why I'm remarking all the time that it is quite important to compress it around that range. Another important thing here, it is about the gaskets, is to choose the correct, in this case, the correct materials. Because at the end, what we are doing is that we are creating a kind of a battery, or we are creating a battery in our case, because we have a metallic surface, then we're adding a different metal, and then we are having the other metallic surface. And then what you're provoking here is that at the minimum that you have like a small kind of current, then you are provoking a battery. And then from those two materials, one will be in this case the cathode, and then another one will be the anode, making it that the anode will start to lose, in this case, mass or weight, and then it will provoke that it will get oxidated or it will get eaten. Meanwhile, the cathode in this case will start to get like more grams or more mass, and then at the end, you could have over there an oxidation layer, making it that you don't have conductivity over that place. So that's why it is really important just to get, in this case, a galvanic list table about materials, and then to choose the correct partner. Because in this case, one of the most common, so just going to an example, aluminum, it is pretty common just to use it on enclosures because at the end it is light, it is cheap, and also it is pretty rough. And then, for example, let's say that we are going to use a gasket that is made of copper, of nickel-plated copper. So then if we check, in this case, the aluminum, it is on this position. And then if we are going to look for the copper or the nickel, actually will be the nickel in this case, we can see that they are pretty far away. So then what will happen in this case will be that the aluminum will start to lose weight, and then the nickel will start to get a bit weighty in this case, meaning that the aluminum will start to get oxidated by the nickel. And then in the long term, and then with long term, it can be a couple of months, 1 year, 3 years, maybe 3 months, maybe a couple of weeks. It can be a bit random because it will be fully depend on the environmental conditions like saltiness, humidity, and temperature. Then what will happen is that the aluminum will have an oxidation layer over it, and then you will have a malfunction of the product over there. And then again, you will have gaps. And then with the gaps, that's not good because the noise can go into the inside or can go to the outside. And also at the end customer doesn't like to see something that it gets corroded or it gets oxidated. So then here, going back to the example that we have the aluminum case, the ideal case will be to choose the same material. So a gasket made of aluminum. Or in the case that it is not possible, then choose something that is pretty close, like something made of cadmium, steel, zinc, or magnesium. Or directly to change the material of the enclosure, that sometimes it's not the best case because it is not possible, and then just change it to something different, or just maybe to plate it with some other material, like in this case, tin, because then you are in the middle of it. And then going back to the gaskets, we have several types of them. We have conductive elastomer gaskets, we have conductive fabric gaskets, contact stripe gaskets, or in this case, metal gaskets, and then we have a knitted wire mesh gasket. So these 4 groups, they are like the most popular ones or like the most traditional ones. And then every gasket, it is meant for one situation. So then if later you come to me asking like, yeah, which is the best gasket to use that it will fit on every situation, on every application? Sadly, my answer will be, it does not exist. Or if it exists, it is not going to be really cheap. So then what I mean with this is that all the gaskets, they are meant for a specific situation. Like, for example, we developed, in this case, or we created already like a kind of a cheat sheet, like the ones that we were using in the high school, just to, let's say, help ourselves during the test. And then here you can already ask yourself the different questions. Like, for example, okay, which kind of value of ingress protection value do I need? In this case, the ingress protection value, it is the protection value in order to avoid like some dust or water to go through the gasket, in this case. So do I need something above 50? So then we can see already that in this case, the metal gasket, which is this one, it doesn't work. And neither the knitted wire mesh gasket. And then we are already suited only with these 2 options. Then the next question that you can ask yourself is, okay, so more or less, which is the temperature range that do I need to have or do I require for my application? Then if your application requires something that is above 90 degrees or 50 degrees because it is close to an oven, because the standard requires it or anything like that, then you can already discard, in this case, the conductive fabric over foam gasket. And then you only have one choice in this case, which is in this case, the conductive elastomer gasket. But then let's say that, for example, instead of being 90 degrees, the temperature range, the top one, in this case, it is lower, that it is like 80, 70. So then we have these 2 different options. But then When you go to your accounting department, they ask you, yeah, no, we need something really cheap, something traditional, and something that is easy to use. So then the best choice will be, in this case, the conductive fabric cover from gasket. So again, every gasket suits for every situation. And also this wonderful cheat sheet that we have here, it is already available in our website. So feel free just to check it out over there and then to use it. Then the next product group that I'm going to jump in this case, it is the EMC tapes. So EMC tapes, they can be split in two different groups, let's say. So we have, in this case, the metallic ones, and then we have, in this case, the textile ones. Then, as the name indicates, the metallic ones, they are mainly made of a metal, in this case, layer. Like in this case, can be aluminum or it can be copper. And then also, going to the other group, which is the textile group, we have only one available for the moment, which is the conductive fabric. And then at the end, the conductive fabric, it is a piece of cloth that the threads inside of it, they are made of a nickel-plated copper, making it conductive in this case. Then, when to use each one of them? Then normally there are only two different decision makers here, or two different choices that will motivate you to choose one or the other one. First of all, at the end, it is again which materials I'm going to make contact with, again, because of the galvanic corrosion or the effect that we explained before about I'm going to, in this case, put two different materials in contact. So I need to choose the correct partner here or the correct match. And then it will be the flexibility. Why the flexibility is a game changer here? Because let's say that, for example, you need to use an EMC tape in order to create the shielding from your cable, because because your application have let's say the typical cable that it is from AliExpress or from some provider that you may don't know in 1 year because they disappear and they don't have, in this case, the shielding. So then, in this case, for example, the conductive fabric, it can be the best option there. Mainly because you can already grab it and then it is more flexible to it. Meanwhile, if you try to grab the cables using, in this case, the copper tape or the aluminum tape, then it will be a bit tricky. I mean, you can do it, but it will be tricky. And then also at the same time, I will personally recommend you to use some gloves because, talking by experience, normally the edges from the tapes, they are pretty sharp. And then also another important thing here is that the EMC tapes made of copper and aluminum, normally they are not really reworkable, meaning that once you apply them, if you, let's say, place them in the wrong place and then you want just to remove it and then use the same piece in another place, probably you will face that over the surface from the copper or the aluminum, you will have already like a lot of wrinkles. And then those wrinkles, depending on the frequency, they cannot be, let's say, in this case, helpful. They could provoke like some unexpected noise or some unexpected EMC problems there. Meanwhile, the flexible one, in this case, the fabric tape, as it is a piece of cloth, you won't face like those kind of wrinkles. Then, and some tips about using the EMC tapes is that, first of all, the conductive tape that we have on the bottom, in this case, it is a conductive glue, that it has some conductive particles or some conductive bubbles over it. So it is really important and vital that once you are applying, in this case, the EMC tape, you need to, in this case, use a roll, or maybe you can just use your fingers and then rub the top surface of it. So then you are ensuring that you are breaking the bubbles and then you are just compressing it extremely good. That's a really important topic because if you just place them and then you don't, let's say, make some pressure over it, then what it can be happening is that you will have, in that case, an open, or you don't have conductivity because the bubbles made of conductive powder, they won't break in that case. So it is something just to have on your minds once you are using them. Then, speaking about tapes, I commented that they can be used in order to create the shielding for the cables, but they are not, but normally you will use them, especially in this case, to avoid the pigtails. Like, for example, you can find over this connector or over this USB cable that we found out over a provider. Then, what is a pigtail? A pigtail at the end is that it is a piece from the shielding of the cable that is directly linked, in this case, to the enclosure, which in this case will be, so the copper layer from the cable, it is the shielding. And then, as you can see here, just a small piece, it is fully connected to the enclosure or in this case to the metal case from the cable, making it that in the low frequency, you will have here a wonderful magnetic field antenna because you will find here a loop antenna. And speaking by experience, this is normally one of the main issues that you could face on the EMC chamber. Once you are going to with your device, and then if you are using a cable that is not really trusted, and then you don't know from where the noise is coming, then my first recommendation would be to check it out the cables, because over there it can be a really nice source of problems in that case. And then what's the best way in order to fix this issue? Really simple. Just grab the whole cables to it. Just grab the whole cable with, in this case, the shielding material. Like in this case, it can be the shielding textile or maybe like some metallic wire mesh. Put the cables to it and then add as many contact points as possible, in this case, to the ground plane or maybe in this case to the housing. And then also be aware or be sure that those contact points, they are ensuring that you have a 360 connection to the enclosure, so that they are like fully grabbing the whole cable to it. This is required because then what you are avoiding by doing the 360 connection will be to avoid, in this case, the pigtails, which is just to have a small piece over there, because then you are offering more path to the noise to go through it in that case. And then also another important thing is to don't paint over the surface where you're going to connect, in this case, the cable. Because then if you are adding a paint and then normally the paints, they are not really conductive, then what you are having is you are just placing something conductive over something that is non-conductive. So be aware also about that kind of problems. Then the next point is going to be the board level shielding. Board level shielding, it is at the end, as the name says, it is the shielding products that we normally use or face in our PCBs. And then in order to improve the shielding from our PCBs, we have two different ways. We can actually just use some shielding, like create our small Faraday boxes inside of our PCB or inside of our device. Or what we can do is just to improve the grounding, just to redirect, in this case, the noise from our PCB to the ground plane or to the housing. And for that one, there are several types of products. Well, there are two different types of products. We have, in this case, the contact fingers, contact springs, or spring contacts, depending on the provider. They are named by several names, but at the end, it is just these feather contacts, or even, I mean, it is just a piece of beryllium copper that is elastic. And then also we have, in this case, some SMT gaskets, which it is the same principle as the EMC gaskets, but in this case, instead of being placed on the cover, what they are meant to be solderable. So they are suitable for pick and place and also to be used on the PCB. But then the main definition of it is the same. It is an elastic core surrounded by a, in this case, metallic material. And then in order to improve the shielding by creating Faraday boxes from inside of our PCB, what we have in this case, it is the shielding cabinets. And also you may know them as shielding cans or Faraday boxes. Then jumping into detail about first of all, about how to improve the grounding contacts or how to improve the grounding from our PCB. In order to choose the correct grounding contact, it is really simple. The things that you need to have in your mind. The first one, it will be the contact point. So at the end, it is important to know from where you're going to make, in this case, the contact. If it is going to be from the horizontal axis or from the vertical one, in this case, because then you can already discard too many different shapes and options. Then another important thing, again, it is the compression of it. So it is an elastic material, like an EMC gasket, and then we need to bear in mind that the best way in order to don't overstress the material, and then also to ensure that we have a good conductivity value or low impedance value, it will be by compressing it around a 20 or a 30%. So what I mean with this is that let's say that you need to choose a contact finger that has to be 8 millimeters because you need to fill that gap. So then in that case, the best way or the best choice will be to choose a contact finger or a grounding contact, just to be more general, that it has a height of 10 millimeters. Because then we have the 10 millimeters, we compress it around a 20%, 30%, and then we have our 8 millimeter original gap that we need to fill. So that's, again, something important in order to have the best value without stressing the materials. And then, as you can see here, there is also This is really important, as I commented, because as you can see, like there are some parts already from this contact finger that, as you can see, they are already being stressed out. And then another important thing in this case will be like for the EMC gaskets, the galvanic corrosion. So depending on where you're going to make contact with your PCB, because probably you are going to make contact from your PCB to another PCB or probably to the housing, then it is really important to know which materials are you going to make contact with. Because again, if it is going to be aluminum, then what you want to avoid in order to avoid any kind of corrosion is to have a contact finger that won't face, in this case, corrosion, because you want to have all the time conductivity. So that's why in this case we have contact fingers made of nickel or contact fingers made of gold, because they are materials that they can withstand a lot, in this case, the galvanic corrosion. And then also another important thing is how to solder them. So SMT grounding contacts, they are suitable for pick and place, but then some of them, they are made of nickel. And then you need to be sure that the bottom surface of the nickel plated contact fingers or SMT contact, they have a small layer of thin plating, because then you won't face any kind of issue during the soldering process, because nickel, it is a material that normally it takes a lot of time in order to solder it properly. And probably you will need to make the PCB go through the reflow oven more than one time or even more than twice. And then again, like for the EMC gaskets, we have a red expert module. So then by checking out our red expert module, then you will have again more or less the same information as for the EMC gasket. So you will be able to find in this case the compression charts, the force deflection diagram in this case, where you will have how much force you need to compress the contact finger or the grounding contact, and how much force is the grounding contact making against your device or making against the surface which is being compressed against too. And then also you will have on the another chart about the conductivity or the RTC in this case. So then you can already see that in this case, once you are compressing it just a tiny bit, you already have the best value of performance. But again, normally the sweet spot is to have the 20-30%, which will be something around this range. And then also at the same time, you will be able to have, or you will be able to find the dimensions and also the solder, the footprint in this case. Now, now we are going to go into in this case, the shielding products or the Faraday boxes that we could find for the board level shielding. Then, as I explained before, for the Faraday boxes, we have, in this case, the shielding cabinets. And then our main goal, it will be the same as we have for our housing. That is just to isolate one small area from the environment, or just to create our little corner or black box where nothing can go into the inside, or nothing can go to the outside. So in this case, what you are improving in this case will be the humidity and also the radiation problems. Because let's say that this IC, it is something really bad that is creating a lot of noise to the environment, and then we want just to mute it, or we want just to, in this case, to kill it. So then what an easy solution, instead of redesigning the whole PCB, will be just to add a standard cabinet, and then everything will be kept into the inside. Just isolating, in this case, the source of all the problems, and then leaving all the victims, that it will be the rest of the components that they are in the outside, just totally free of any kind of problem and also of any kind of possible interference that it could create. And yeah, and also it will happen the same with the other way around. That let's say that we have the source of our problems in the outside, sorry. So then by placing it into the middle, or just by isolating in this case, our victim, then we will avoid it to be affected by some other device or some other field that we have in the outside. Then for the shielding cabinets, there are several types of them. One of them, it is the traditional ones. Why they have the name about traditional? They have the name or the undername of traditional because about how they are being manufactured. That is that we get the metal sheet, and then what we are doing is that we are just working the material by bending it. Then by doing this, we have like some small corners on the edges, like you can see here, here, or there, that they are really tiny apertures, that in the low frequency range, normally they are not a big problem, or they are not creating any kind of problem. But then once we are starting to work with high frequency applications like 5G or even for radar applications, then these tiny corners here, they can already be an open door for the noise or for the signals or for the fields to go into the inside or to go to the outside. And also not only these tiny gaps that we have here, also these tiny apertures that we have designed in order just to allow all the traces to go to the outside and to the inside. So that's why we name them traditional and normally why they are used for the low frequency. And then also we have another version of the shielding cabinets, which in this case, they are fully seamless. And why they are fully seamless? Because how we are producing them, which what we have is that the material, we have it here, and then we have, in this case, a mold, and we are just compressing it really slow to have a deep drawing of the tooling or the mold into the material, making it fully seamless. And then what we are doing at the end is just to cut the edges. So then we have a fully seamless piece of metal, making it suitable for high frequency, as I commented, because we don't have any kind of gap. So we have a perfect Faraday box that is soldered to the PCB. And then this kind of cabinets, they are perfectly for the new technologies and the new projects that probably you are already working on. Like they are related in this case for IoT, IO-Link, DNS, 5G applications, or like the new standards like the 6G. Then here you can already see a clear example that of a measurement that we did with ANSYS, with our simulation tools, where we compared a traditional cabinet like this one against a fully seamless cabinet. And then we measured it. What we have in the insert here, it is a microstrip line that goes from here to there. Sorry. And then what we have over there, it is the microstrip line that is generating noise or a signal in a constant way. So then as you can, if we compare them, then we can already see that on the left, we have all the noise to come out from the small apertures that we have here for the traces. And then also in the inside, we are having like some reverberant chamber noise in this case. Meanwhile, if we compare it to the fully seamless cabinet, what we have here, it is just everything just deep or fully calm, meaning that all the noise is being kept in the inside and then it is being muted in the inside. Then some tips about shielding cabinets. One of the first things that you need to have in mind is that at the end we have a metallic piece, and then normally metallic piece, when you place them in the outside, like you have your metallic fence or you have like a metal pole in this case, it gets oxidated just by the humidity of the environment or maybe because of the saltiness of the environment or something like that. And then the standard cabinets, normally they are made of tin-plated steel. And then the tin-plated steel, especially on the edges, it gets corroded or it gets oxidated extremely easy. Then this oxidation problem, it won't affect, in this case, the shielding effectiveness. It will only provoke two side effects in this case. The first one, it will be that it will be more difficult in order to solder it to the PCB. And then the second one is that it won't look as good to the end customer. So then, as we commented before, the end customers, they want something that is fully colorful, like stylish, polished, and it looks good to the eye. And then if it is oxidated, probably they will think that it is not as good as maybe some other or brand new product. So, but the main thing is that they won't affect the shielding performance of the cabinet. But anyway, let's say that you need it for the end customer. So then the material that is being used can be changed from tin-plated steel, in this case, to nickel silver, which it has a higher performance or a higher resistance against corrosion. Meaning that, as you can see, so these two cabinets, they were exposed to a salt spray test that we did internally inside of the company. And then as you can see here, there is no sign of corrosion into the nickel silver cabinet, because the nickel silver, it has a better capability to deal with the corrosion and also to the humid environments and also to the salty environments. So that's why we normally recommend these kind of materials when the end application is going to be placed, like for example, next to the beach or to a salty environment, or in a really humid environment, or even to the automotive sector normally. Then another important thing here about the shielding cabinets is to use as much as the standard dimensions possible. Why is this important? Not only because we have over 260 standard dimensions, it is mainly because of a matter of cost. At the end, the shielding cabinets, they can be customized, and then they can be customized to create any kind of set that you need. Like we can make it with inside compartments. Also, we can make it with a specific set for you, or even with different kind of materials. But at the end, we are working metal, and working metal, it is not a cheap thing to do in this case. meaning that there will be some cost needed here. And that's something that normally it is not suitable, especially for samples. So the advice here will be to have in your mind that probably you will need a shielding cabinet from the first time. So the advice here is to add already the footprints to the areas which you think that they can be a bit sensible or that they can be problematic in this case. And by just having in this case the footprint, then once you are, for example, in the EMC lab, and then you know that you have the problems with that one specific area, by having already the footprint, you can already make the test and then just try, in this case, the cabinet without having to wait weeks in order to have the prototype for a specific cabinet because you didn't think about it in advance. So that's why it is really important to have it in your mind since the first moment. But then, anyway, let's say that you are already running some projects, then the next week that you are going to face the EMC labs, and then you are not fully sure if you are going to need a cabinet. So we have a solution for those kind of situations where you are not really sure if you need a cabinet, but you may need it. So here we have a wonderful pack, which in this case, it is some shielding clips that at the end is just a clamp to be soldered on the PCB. And then we have a do-it-yourself, in this case, a piece of metal that you can, with this one, you can create your own shielding cabinet. And you can create it by just, in this case, just getting the metal layer or the metal sheet in this case, and then just bending it. Because just with your bare fingers or maybe with some clamps, you can already just bend it and then create the set that you need. And then you can solder the clips in this case to your PCB by just scraping a bit the solder paste and the solder marks, but by just leaving in this case the copper plate. Then you can solder the clips like these ones because they are really small. So only with a tiny drop of tin, it will be already soldered. And then you can, with your pre-design or like handmade shielding cabinet, you can just fix it to your PCB. And then as this will be connected probably to your ground plane, then you will have everything fully connected. And then with this one, you can already find out if you will need the cabinet or not in a short time, and then without having the need to request for sample for mass production or to invest money and time into the samples. And it is something that can be done in the same day. And then the good thing with us is that once you have like the draft for the cabinet that it can be done with the do-it-yourself, then you can just come to us and then we will fully create for you the mass production cabinet in this case. And now I'm going to jump to the magnetic absorbers, which is normally the products that they are fully related with black magic because they are a bit complicated or a bit, let's say, out of thinking or out of the standard. So one of the main things that we need to have clear, it is, as we commented before, it is the permeability. The permeability, as I explained it is the capability of the material to play with the magnetic field from the environment. And then, as you can see here, once we have here a magnetic field, and once we are adding a magnetic material, like in this case, it can be a ferrite, then we can see that the lines from the magnetic field, they are being affected, mainly because of the permeability of the material. Then the permeability, actually, it has two different components. It has the reflection and it has the absorption. So the mu prime, as I commented, it is reflection, and then the absorption, it is the mu double prime. The reflection, it is the capability of the material to redirect, in this case, the magnetic field. And then normally it is quite high in the low frequency or at the beginning. And then the absorption, in this case, it is the capability of the material to absorb the magnetic field and then to transfer it into heat energy or just to transfer it to heat. Then with heat, what I mean, it is not that you will have a small thermal generator over there. Is that maybe in this case, the absorber, instead of being at 20 degrees, it will be maybe at 20.1 or 20.01. So it is not something really, let's say, dangerous for your application. Then why the permeability is important? Because at the end, you will be able to find that not only in our website, everywhere you will find that there are different types of magnetic absorbers. And then all of those different magnetic absorbers, they have different values of permeability. And then those values of permeability, they are mainly provoked or they are very noted in this case by the mixture of magnetic materials like the ferrite, the manganese, and some other materials that are into the fixture, and also how the flakes they are being oriented. And then every type of mixture, it is like the secret portions from Asterix and Obelix, that every material or every mix, it has some specific specs. Like for example, you can see here that our 304, it has a low value of permeability, but then if we compare it to our 344, then that is just a different mix, then the permeability or the capability to reflect the field, it is way different. And even it will be the difference, it is even more notable if we compare it to absorption in this case. Then, where can be the magnetic absorbers being used? That it can be a question that you could have in your minds currently. So magnetic absorbers at the end, they can be used in several applications, or actually normally it is totally up your imagination because we have seen too many different things. Like for example, one common application can be in order to clean the noise from your trace, in order to avoid like the crosstalking or to have like some ringing noise into your signal data. So as you can see here, by just sticking it into the trace, then by the capability to absorb the noise, they will be able already to clean a bit the trace, or to clean in this case the ringing effect that you will have up there. And then let's say that in this case you have your housing, and then you detect it already on your EMC lab or just with your measurement equipment that inside of your device you have some noise that is being provoked by a device that you don't know which one it is, and then you have already the situation that you have already mass produced the PCB, and then you cannot redesign it. So then a solution can be to just stick it, in this case, the magnetic absorber inside or in the middle of the housing, and then by, again, the permeability values, it will be able to absorb the noise or just to redirect it or just to shift it to different frequency range. And then by doing this, by just sticking it into the housing, then you will be able to save the rest of your components from the noisy area. Then I'm saying all the time that you stick it over the surface or just stick it over the trace. In this case, the magnetic absorbers, they are being composed by a layer of in this case, the magnetic mixture, and then on the bottom of it, what they have, it is an adhesive layer, a non-conductive one, to ensure that you won't have any kind of shortcut over it. So then it is really simple. It is at the end like a football sticker that you can just remove the release tape, just stick it wherever you think it is needed, and then check it out. And then if it is needed, then you can just leave it over there and then just request the mass production of a specific shape. And then in the other way around, that you place it in one place and then you're not really sure if it is needed, then you can just remove it and then just stick it somewhere else. Another important thing here is that they are really handy. And with handy, what I mean is that you can just grab the product in this case and then just cut it with your bare scissors. Because for that one, there are two different types of magnetic absorbers. The first one, it is the flexible absorber, which is in this case the grayish one. And then this one, it is a mixture between magnetic powders with silicon. And then we have the flakes from the ferrite powder, just like orientated to some specific shape. So then we have the different values of permeability. And then the good thing is that as it is mixed out with in this case, with a silicon material, then they are really flexible. And with flexible, I mean that it is like the paper that you are currently using in order to write notes, that you can just bend it, flex it, and then you can just cut it with your bare scissors or just with a sharp edge or a sharp tool in this case. And then neither the permeability values or neither the performance of the product will be affected by it. And then there are some other type of products that it is, in this case, the flexible sintered ferrite sheets, which is something that we name it normally just to make it shorter and faster, FSFS in this case. And then this product at the end, it is several layers of ferrite powder, just place it one over the other one, and then just smash it together them until we make a sandwich. And then all of those layers, they are placed over an adhesive paper. And then on the top, in order to protect the magnetic powder or the pre-cracked ferrite plates, we have a PET layer, just to avoid like any kind of scratch or damage. Then a big difference between the flexible absorber and the FSFS is that the FSFS, as it is almost a ferrite plate, then they are not really flexible. You can bend them a bit, like you can see on this picture, but then if you test the water a bit more and then you try to bend it a bit more, just creating a more close angle, then what you will be provoking is that the material will break. And then you will be able to hear a cracking noise and able to feel it with your fingers. And then this is like in your life. When something is breaking or when you can hear a cracking sound, normally like your brain is going to tell you like something is not good because you are breaking something there. And then this rupture or breaking, what will provoke is that the magnetic properties of in this case, the magnetic absorber will be changed. So good things and bad things about between these two is that flexible absorbers, they are flexible, so they can be reworkable, but then also the permeability values, they are not that high compared them with the FSFS. While the FSFS, they have a higher value of permeability, but they are not that really flexible. So there is all the time a win and a loss, depending on your needs. Then some other applications about where to use the magnetic absorbers. They can be used, for example, in order to kill or to, in this case, remove problems between interdecoupling and interdecoupling problems. The main difference between them is that the intradecoupler problems, they are when we have the noise of source and then it is affecting something in the same level or in the same PCB. So it is something that mostly affects horizontally. Meanwhile, the interdecoupling problems, it is something that it affects in the vertical axis, so in different layers. So this problem, it is quite common to have it, like, for example, in server racks, where you have several PCBs stacked one over the other one, and then one IC from one PCB, they can be affecting some other PCB in this case. While the intra-decoupling problems, normally they are the ones for the typical PCB. When you have, for example, your iPhone or your mobile phone, and then something is creating noise in the same level or to the component next to it. And then another application, or a really popular application in this case, it is the wireless power applications and NFC RFID or NFC RFID applications. Which, for example, if you just grab your phone or just grab your wireless charger, then you will be able to see that you have a wonderful wireless coil. And then on the bottom of it, you will find that you have a ferrite sheet, or like in this case, a blackish or a dark sheet in this case. And then that material that I'm just remarking now, it is actually it is an FSFS or a ferrite sintered sheet. And they are really common to be used on these kind of applications, mainly because once you are designing your NFC antenna, then you are designing it normally in a perfect environment when you are not thinking about, for example, the battery from your phone, or maybe the metal case from the housing, or maybe like the metal case from the door or from the wall where the device is going to be placed over it. And then once the magnetic field from the antenna is facing that metallic layer, what you're provoking an effect named in this case eddy currents, which is an electric field, and then this electric field at the same time is creating this red marked magnetic field. So what you are doing is that you are adding an unexpected magnetic field to your system. And then this magnetic field, what it's doing is that it is shifting your signal from the frequency range. So instead of having it tuned to the standard that is 13.56 megahertz, you are shifting it to the left or to the right, depending on, in this case, the electric field. And then what you are normally using is this kind of material, in this case, the ferrite plates, like this one or this one, because what you are doing is that you are placing it between your metallic surface and your coil. And then I like to explain it that it acts, in this case, like a mirror. So what you are doing is that once the magnetic field from the antenna is facing the ferrite, it is being pushed or redirected against to the top. So it is not getting to touch, in this case, the conductor surface. So we don't have here the eddy current and neither the unexpected electric field. So the whole system is fully controlled in this case. So by doing this, you are able just to remove, in this case, the stiffness, or you are able to correct, in this case, your signal. And then in most of the cases, what you are doing at the same time is to amplify, in this case, the power or the amplitude from your signal. And then by this, you will improve your communication system. Again, Now, probably the question is, okay, so then which one should I choose? Because you commented that you have several permeabilities, you have several factors, you have several applications, so there are too many. Sadly, yes, there are too many. But then the best way to know which one you have to choose, it is first of all to check the permeabilities, because then by checking the permeabilities, you will be able more or less to sort it out which one do you need depending on your frequency range. With this, I mean that let's say that you have an application that is facing problems over 100 megahertz, and then you will need to attenuate something or to absorb a lot of noise over that range. So then you already know that maybe this absorber sheet or this magnetic absorber, which in this case it was the 344, if I remember correctly, then you will have the best performance. So once we know which one do we need, then the second step will be to call our colleague from Würth Elektronik and then ask for samples. Ask for samples from the different thicknesses, for different permeabilities, like for example, this one, and then even the red one and the gray one, and then try it in your device. Why I'm saying this? Because at the end, the value of shielding effectiveness, the one that I explained at the beginning, it is solely a reference value. And then it is a reference value that will depend on several factors. Like in this case, it will depend on the measurement setup. It will depend also, for example, on the distance about the source and the noise. It will depend on your application. So it is something that you cannot control. So then the best thing is just to ask for the sample, use it on your application, and then run a measurement and see if it works or if you need more or if you need less. A rule of thumb that I explained before at the beginning is that normally for magnetic materials, the thicker the better in this case. So a practical example will be that let's say that we know that we need to use this material, the one that it has this permeability or this mu double prime. So then for this one, we probably will have three different thickness, 0.1 millimeters, 0.2, and 0.3. Let's say that you use the 0.1 millimeters, and then you almost get to the right values. So you almost kill all the noise from the conductive emission test or from the radiation emission one. So then try the one that is thicker, the 0.3. Probably that one will help even more. Because over there, normally this is what we were explaining before. That in this case, the thicker the better, only for shielding attenuation. Because the permeability, again, it is a value for the material. So meaning that the value of permeability will be the same no matter the thickness, no matter the dimension. Then, also at the beginning, I said that a common problem or source of noise can be, in this case, the heat sinks. Then also we also have a solution. There are also solutions on the market in order to help to dissipate or to remove all the problems that the heatsink can provoke. First of all, going to the basic, a heatsink can be an antenna at the end because what we have, it is a really nice metallic surface that is making contact, in this case, with another metallic surface that it can be the PCB or the CPU. So you have over here a metallic surface, a blank space, or an air, and then here you have another metallic surface. So you have over there a capacitor. And then that capacitor, it can create some unexpected problems that maybe you didn't think about it in advance. And then probably the first way of act will be, okay, so maybe I can remove the heatsink. And then your colleague from the mechanical engineering will reach you, say like, don't do it. The whole thing will just melt. So then the heatsink is a must. Then there is a solution that is normally the gap fillers or the thermal materials in this case, but they are not doing anything from the EMC point of view. Actually, they are just adding like more space, so they are changing the capacity effect here. So then that's why there are some flexible absorbers that they have some ceramic powder into it. So it is a mix between an absorber and also a thermal material, meaning that by placing them in the needle, you will be able to, in this case, absorb the noise that the heatsink could be provoking or that this capacity effect that you will have here. And then at the same time, as it has ceramic powder, you will be able just to conduct or just to redirect all the heat from your IC or from your CPU, in this case, to the heatsink, to make it go through the absorber and then to the heatsink. And then again, everything that I have been talking about, like permeability, the mu prime, the mu double prime, and also some measurements, you will be able to find them into our red expert module that is about the magnetic shielding. Then these measurements that you will see here about the shielding effectiveness, it is a measurement that you will be able to see the setup here by just clicking on this tab. And then it will be the measurement that it will be the closer, in this case, to this application to this application. In this case, to remove the signal from the trace, meaning that these two charts that you can see here, it will be the noise that in this case, the absorber is removing from a trace, in this case, from a microstrip line. And this will be the noise that we measure it with a magnetic field antenna, and this one with an electric field antenna. So then you can already more or less sort it out, which one do you need or which absorber do you need. And then last but not least, and here in the last 2 months, I will say, we released a new product to the market, which in this case, it is something that we name the EMI absorber pads or the EMI pads. And then here what we have, it is a layer of magnetic absorber over a metal layer, a metal layer over a magnetic absorber. I say the other way around. So then here what we have, it is an electric layer or a low impedance conductive layer with a magnetic layer. So then you are able to, in this case, to kill two birds with the same shot, meaning that you are able to use this material no matter the problem that you have, meaning that it will be able to eat or to remove the electric field by the aluminum layer, and also at the same time the magnetic field by using the magnetic layer here. And then also for the times when you need to avoid like any kind of shortcut or to improve the ESD from your application, then we have it also with a version with the PET. Then some important information about this product is that, again, we can produce it on different type of application. I mean, with different type of shapes, like on a roll, on a sheet. Also, we can change at the end, like the thickness, we can change the magnetic layer to make it to the right level of permeability. We can change the material. We can add some extra, in this case, PET layer or some extra adhesive layer to make it sticky on the top and also on the bottom. So it can be fully customized in this case. And then the good things about it is that it will help for everything, as I commented before. So first of all, it will be able to help to mitigate all the EMI problems that you may face, even for the intra-decoupling or for the inter-decoupling. And then at the same time, as we have here, in this case, the magnetic layer, it will help out, in this case, to dissipate all the heat that maybe your IC will be having, or maybe a ground plane from your PCB will have. Meaning that you can just place here a thermal interface material to make it contact with the housing, and then you will be able to attenuate all the EMC noise or MI noise, and then at the same time to transfer all the heat from your IC to the heatsink. And then last but not least, another, maybe you are thinking, okay, but you have over there a metal layer or a metal plane that is not connected to the ground plane. That's dangerous because then you will have a floating ground plane. Yes and no. So you will have it, but in the measurements that we did, then we designed this magnetic layer over here in order to attenuate this effect of the ground plane. And then in the worst case scenario that you want to connect it just to be sure, then that's why we have the no PET version, so the no isolated version, meaning that you can connect the metal layer directly to your ground plane by using, for example, the aluminum tape that we have in our portfolio. Then everything, it is already published in a paper that we published in the EMC Europe Congress from Europe. And over there, you will be able to see the measurements and also the measurement setup that we have it doing. And then these are some real measurements where we compare the magnetic absorber that we use it on this product versus the whole product itself. And then when we measure the shielding effectiveness, so the electric field plus the magnetic field, then we can see that there is not fair competition between them. Because in this case, the measurement or the level of attenuation that the new product, the EMI patch has, it is way better than the one of the absorber only. So that's why this product, it is like an all-around product. And then at the same time, it can be used as an alternative for the cabinets. Because as you can see here on these charts, there is a difference only of a few dBs of attenuation. And then the good perks or the pros about this product at the end will be that the EMI pads, At the end, it is a sticker. So then you can use it on your application, no matter that you have the footprint or not the foot, or neither you have it. Meaning that if you don't want to redesign your PCB because you're already on the last stage from your device, but then you need something close to a shielding cabinet in one specific area, like an AC or a trace or an inductor or a clock or anything like that, then you can just cut a small piece of this material, stick it over it, and then you will have the same level of performance. So it will be a natural alternative that it won't require you to redesign the whole PCB.
Thank you so much for joining us as we navigate the complexities of EMI with shielding. And of course, if you'd like to learn more on the subject, we urge you to visit our video center. It's under the News Center section, available at Würth Elektronik online. While you're there, you can also check out the lineup of EMC shielding materials like EMC tapes, gaskets, grounding, and board level, and magnetic shielding. You can also find a variety of EMC components, ESD protection, thermal management, and power magnetics, all at www.we-online.com. You're listening to Würth Elektronik's What's Up Radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik technical specialists. We're going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast.